And so we're going to start with a picture like this. Anybody know the name of that shape? It's a parabola. All right? That is the graph of a quadratic. Quadratic is something where we have that squared part as our highest exponent. But usually we just call it a parabola. All right, and what we're really interested in here is this general form. So remember we had standard form of a line. We have a standard kind of general form of our quadratic. So y equals ax squared plus bx plus c, where a, b, and c are integers. And down the road, we're going to use that form, and we're going to complete the square and get the quadratic formula. But for now, we just have our standard form. And what we want to find are intercepts. So where this graph is crossing the x-axis. All right? So what does that mean algebraically? If I put in this number, let's put in this one. This is a negative 4. If I put in negative 4 to that graph, what is my output? What do I get out? What's my y value? 0. Same thing here. This is my intercept. These are numbers that I plug in and I get out 0. So values for x, which gives y equals 0. And we call these roots. If I was to factor it, I would get my general form. So if I have p and q, what that means is if I put in p, I get out 0. If I put in q, I get out 0. This is called the intercept form of a quadratic. So we have two forms already. We have the general form, our standard form, and then we have the intercept form. And just like we have for a line, slope, intercept, it's the same idea here, right? Except instead of the intercept being the y-intercept, these intercepts are where it crosses the x-axis. These are values that I put in and I get out as 0 from my function. All right, so for my example, if x is negative 4 and y is 0, and x is 0, if I know those are the intercepts, I can put them in for p and q and get my general form of a line. All right, subtracting the negative would leave me with the x plus 4 here. This would just be x. And I don't have a value on a yet. I would need to plug in another point to actually solve for a. But just like before, we had a line and we wanted y equals mx plus b, we could solve for b if we had a point. All right, so if I set it equal to 0, this could often be 1, but sometimes it will be different. We could find it and check it. We have these things called the roots. All right? Let me go back to that, sorry. So I'm asking for the roots of this equation. The roots would be negative 4 and 0. Those are values that I plug in and I get out a 0. So here's our general goal for these parabolas. I want to find values for x that give y equals 0. And we're going to use something called the zero product theorem. It sounds scary, but it's really pretty easy. What operation does product mean? Multiplication. So that's a zero multiplication property. If you have things that multiply and it equals 0, that means that one of those things or all of those things have to be 0. So if I just have multiplication, which I do in this case, it equals 0, that means either a is 0, this is 0, or this is 0. Not yet if you agree that has to be true. Yeah. There's no other way to get 0 unless you're multiplying by a 0 somewhere. So if x minus q is 0, what does x have to equal? Q. And if x minus p is 0, x has to equal p. These are called either the zeros or the roots. So if I ask you find the zeros of this equation or find the roots of this equation, I'm asking you to find the values that you plug in and you get out 0. All right, well, what about if a is 0? What happens to my whole equation? Yeah, everything zeroes out. I don't have a quadratic because if I distribute a 0 through, everything's going away. I don't have a nice parabola. So a can't be 0. So a is some non-zero number, but I have these two components that give me my roots. All right, so that's key to understand what we're doing here. We're looking at a graph. We're finding the values you put in to get out of 0. Thumbs up if you're still with me. You should be, hopefully, yes. All right. Now, it would be really nice if it was always like one thing times another thing, and then parentheses, and like x minus 5 and x plus 2. But it's not going to be that way. So what do we have to do? We have to factor. So if I have this, I need to determine the roots. Well, I can't use the zero product theorem because I have subtraction here. It's not 0 and 0, right? Well, it could be in this case, sorry. But I don't set this equal to 0 and this equal to 0 because I have a subtraction. I got to get multiplication. So who sees what we can factor out of this thing? X. So I'm looking for the greatest common factor. And then I want to undistribute or factor that out. So in this case, it's x. You pull it out. And now I have something that looks like the zero product theorem. I have just multiplication. So it means that either this piece is 0 or this piece is 0. So x is 0 or x minus 5 is 0. Which means that x is 0 and x is 5. Those are my roots. How could we check it? What's that? How do we know that we got it right?
Plug it in.
Plug it in, yes, thank you. You plug it in. And that works out to be true. And 5 squared minus 5 times 5 is 0, so it checks out. All right, so it's an easy check. And it's something that we can determine and know if it's going to be true right off the bat. All right, so that one's pretty simple. But it's not always that simple. So I want to talk about kind of 3 ways you could look at this problem. And you've done this before, so you don't have to write it down if you don't want to. But what we're going to do is, if I was to multiply this, there's 3 ways I could go about it. And then if I want to factor it, can use those 3 ways in reverse. So there's 3 methods that you could look at. One is FOIL that you guys are familiar with, double distribution, and then the geometric interpretation. So if I FOIL it, I do the first, what are my first terms in this case? X and x. So I get x squared. My outside are x and 2. So I get 2x. My inside, negative 4 and x. And then the last is negative 4 and 2. And I add them all up. And simplify. All right. FOIL is just a method that really utilizes double distribution. So this is kind of what Tom was saying earlier. And there's my FOIL acronym. If I was to take this and something multiplied out the outside the parentheses, I can push it through, distribute it once, and then I can distribute again. So there's my double distribution. And it simplifies to the same thing. All right. The last one is one that you may not have seen before, but it's just a different way to think about it. I like to sometimes think about it in this way, but it's a geometric interpretation. So if I started with the rectangle, and I made my side lengths the length of my factor. And then I find the area of each of these rectangles or squares. What's the area of this upper left one? X squared minus 4x minus 2x. If I add them all up, I get the same thing that I had there. All right? So this method is not very, the double distribution is not very useful for going from this to that. This FOIL is not even that useful for going from the expanded to the factored. But the last one might be. The last one might be for people. And I just want to throw out as many as I can, and you guys will kind of pick what works for you. So if I was to factor this is the general method for how people do this. This is kind of what Alicia was talking about. So I have x squared minus 7x plus 12. Well, I want it to look like this. X minus P and X minus Q. And I know some things that have to be true. P times Q is going to be 12. If I think about it in terms of FOIL, my last terms give me the constant, right? If I multiply them out. And what do I know about P plus Q? They have to equal -7. So now basically I can guess and check. All right. I can also set up my geometric model. I know that I have an x squared there and a 12 there. And I know that these two pieces have to give me -7 when I add them up. So, that one's simple. X and 2x. And this model sometimes is helpful when you don't have 1x squared. If you had 2x squareds or 4x squareds, it'd be easier to set up this way. And what I need to do is I need to look at the factors of 12. Plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 4, plus or minus 6, plus or minus 12. Some combination of those is going to go in these two boxes. And I'm going to get 7. So which ones are going to give me 7? Yep. So they combine for -7. That's got to be my -3, -4. There we go. So my factored form would be x minus 4 times x minus 3. Now, if you can do it without the geometric model, if you can look at it just algebraically and guess and check in your head, that's totally fine. But it's another way to set it up and think about what's going on. All right. Now, just looking ahead a little bit, are we guaranteed that everything is going to factor like this? No. When it doesn't factor nicely, we're going to have to use the quadratic formula, which we'll talk about in a bit. And sometimes it's not going to factor where we have real solutions. That's where our imaginary numbers come in. But not till Wednesday. Okay. So there is our intercept form. We have a couple of special cases. If I was to expand a plus b times a minus b, I get a squared minus ab plus ab minus b squared. And so I'm left with a squared minus b squared. That is a difference of perfect squares. That one you will see a lot. So if I had x squared minus 9, what does that factor into?
X minus 3x plus 3.
Right? It's a difference of squares. What's tricky about it is you don't have the middle term explicitly there. So you know things have to multiply to -9 and add to 0. Well, these add to 0. All right? So we call that the difference of perfect squares. And there's my example. All right. Now, if I took a plus b quantities squared, nod your head if that's equal to a squared plus b squared. Good. You're more on the ball than the pre-calc kids this morning. All right. I can't distribute an exponent, but I can expand it. So it's a plus b times a plus b. I get a squared plus 2ab plus b squared. It's similar for a minus b squared. I expand it out and I get a squared minus 2ab plus b squared. These are perfect square trinomials. Trinomial, 3 pieces. What's the general word for a nomial? Polynomial. Just like we have polygon, right? So these are trinomials, 3 pieces, binomial, 2 pieces, monomial, 1 piece. And then after 3, we just say poly. Okay. The book also has a couple of problems on perfect cubes, but I can't find where